So welcome to this first lecture of MCS 472 on industrial mathematics and computation. So welcome and thank you for your interest. The main purpose of this recording, of this pre-recording and of this first lecture is to explain what this course is about, what's the content, and what are the expectations. So that will be the first important and perhaps the most important part of this lecture. And I will briefly go over the computational tools, mainly the programming language Julia and the Jupyter notebook, mainly about installing issues. We will learn Julia and the Jupyter notebook as we go along. So I will briefly say that in the second part. And we will solve 4 problems today, or indicate potential projects, industrial projects that may result from this. The 4 problems are an opportunity to introduce or to recall 4 statistical distributions. Okay, let's go into this. What is this course about? So it is a new course, or it's the first time this course runs under the 472 number. For me, it's not a new course. I have organized the course or offered the course 3 times as a special topics course. So here is the catalog description. First line, technical writing and oral presentation. We will solve problems and work on projects, but most importantly, you get rewarded and compensated for what you can present. So the technical writing and the form of a technical report and how you present your results matters a lot. So that comes essentially first here. So it's last, but if you start solving problems, it's good to think about already about the writing. We have several topics from engineering, from economy, from mathematical modeling, and from scientific computing. So there are some prescribed topics, but most importantly is how you can apply them in the setting of problem solving. So this is a computational course and you will have to use computers and computing. The formal prerequisite is 471, numerical analysis. But what is written here in red is most important. It's most important that you as a student have some desire to solve practical, real-world problems. And using mathematics in doing so. At this point in time, you have already, even if you do not really realize it, you have already been exposed to a vast amount of mathematics. And mathematics is extremely useful in solving problems. That second part you may not yet realize. So 472 is the third course on the computational track, following numerical analysis, and numerical analysis here follows also symbolic computation. What's the central problem in symbolic computation? Well, the expressions are starting to swell, and we may end up with several expressions for the same thing. Expression swell and normalization are the 2 central problems in symbolic computation. We will see some swelling already in this lecture. Numerical analysis is concerned with conditioning and stability of algorithms. course. We will also see that sometimes the 64-bit floating point arithmetic may not be sufficient. If you have not taken numerical analysis, or even if you have not taken symbolic computation, then we will see these courses again in another perspective, so in a more practical perspective. So for 320 is introducing to software, so in particular the Jupyter notebook should already be familiar, but if it is not, then we will see plenty of examples of using the Jupyter notebook. In numerical analysis, we study algorithms for solving scientific problems. If again that is not yet clear, or if you are taking it concurrently, no problem, we will see plenty of examples. So in this new run of the course, it is okay to take 320 and 471 concurrently, or even out of order. Okay, the course is based on a textbook of Charles McClure on modeling in industry, science, and government. What is important about this is that regardless of what your future career will be, whether it will be in industry, in science, or in government, you will have to solve problems. And you will have to work in teams. And it's not so that you have a theory and then you have some examples, and then there is a problem that on an exam you have to solve, and there's only one exact outcome, and that's it. No, a problem is usually open-ended, and it's formulated within the context of a project that you cannot solve on your own. You have to have help of other people. So the teamwork is also encouraged in this course. There are 3 parts. The first part starts with statistics. So today we will introduce some of the statistical distributions. We will see how to acquire data, how to analyze data. So, and that first part will end with a week of project presentations. So that's our first milestone. If you look at the list of topics and the syllabus that's posted at the course website, you will see that there are 3 weeks that are blocked off for project presentations. So the first project will be on describing data. And this explains why we start with statistics. Many real-world problems have dollar amounts in there. So the topic of the second project will most likely be a cost-benefit analysis. Here is a question. Does it ever pay off to go to graduate school? Does a PhD dissertation pay off? So that could be a topic for a second project. Might be for you if you are now have required senior status. This might actually be a relevant question for your future career. So for the first 2 projects, you will be given a selection of potential topics and titles. You can also choose outside that if you have my approval for this. The last project, so in the third part, we will do more engineering mathematics, mathematical modeling with partial differential equations, and also an introduction to machine learning. That last project will be your main project that you will have to solve individually, and that could be a topic of your own choice. So it should be one of the goals of the course is that you kind of will discover what it is that you really want to work on. So in the previous runs of the course, one of my former students decided to enter an MBA program, discovered his entrepreneurial self. So important here, the bottom line is that this is a problem-oriented course, project-driven. So we have specific topics and there will be a midterm exam, there will be homework, there will be final exam, but it's not so much the particular technology or the particular mathematics that you know, but how you can apply it. So this brings me to the expectations. So there are three aspects of this, and again, for the three aspects, you are strongly encouraged to work in teams. So there is the translation or the selection of the mathematical model. What are the assumptions? What are the parameters? Then there is also the selection of the proper scientific software. So there will be a computation that is being done. What software is as important of how can you trust the results? Sometimes software is used in plural. We are relying on numerical computations and on symbolic computations. So there is not one unique model. There's also not one unique software that will do it. The third step, and here it's listed as the third step, but it's actually the first step as well. Make sure that if you get a problem, that you can write it in your own words, and that you can talk about this to your colleagues. So you will have to write reports. A report, it sounds like something that could be 10-20 pages, but it can be a lot shorter as well. The in-class presentation, it seems now that getting 50 minutes full is a lot, but it is not. And by the way, as you are watching this pre-recording, and as we will meet online on Monday, how does this work actually in class? This course can run hybrid, also asynchronous. It's actually okay, and actually also a very good practice to pre-record a presentation. I will also help you with this. So that's also kind of why would you take this course, and rather than looking at the online lectures and reading a book, well, you have access to me. So I will, as much as possible, be available to help you in this transition from the conventional way of taking a math or computer science course into a problem science course. It's, after all, also a computational course. So there's not much programming involved. In the second part, I will say something about the installation issues, but there is the cloud, there is CoCalc. If you have taken MCS 320, you may have used CoCalc the entire semester. You may also have done this in 471. If you're new to all this, do not worry. The environments are very intuitive. And, well, intuitive, there's always a stumbling block. So again, I do not want to trivialize the previous two courses, but it is not super difficult. All software that is listed here is intended for use. So there is Octave, which often is already, if you're a Linux user, we are in the free and open source world, then it might already be pre-installed. Sage is available in the cloud, and there is also the Python framework, the ecosystem, NumPy, SymPy, SciPy, and now I forgot Matplotlib. And then there is Julia and Jupyter Notebook. So in this course, we will mainly by default use Julia and Jupyter, but already today I will use a feature from SciPy. Okay, how is the evaluation being done? What is inescapable are the projects. So there are 3 weeks blocked out for project presentations. If you are a little bit shy in the beginning, work together in a team, and it's okay if one member of your team presents. You can alternate. If 10 minutes seems, or 15-20 minutes seems too long, somebody can do 10 minutes and the other person can take over, or you can alternate. So projects are important, but there is also homework, and there are exams. Homework is important for you to get feedback on your first cut on a problem. So I will, on the slides, there are 4 exercises that will be collected at some time. I will tell you how to do the exercises. So the purpose of the pre-recordings is also that you can go back to the pre-recordings and hear me explaining how you should handle this problem. So the homework problems are toy problems. Usually they are very conventional mathematical problems. Just we have some theory and we want to have an example to illustrate the theory. Even though I will play the game here today that we have a problem and then we find the right mathematical context. It's important that you can write your own solution, that you can explain your own work. So collaborations are encouraged, and we have an enormous wealth of resources that is available. But if you submit a solution, it should be your own work, or you should properly cite your sources. So there will be one entire lecture on how to write the project report. Citing and giving proper credit to your resources is also important. There is a homepage for this course where all the links to the information and the links to the pre-recorded lectures will be posted. Okay, so this is the end of the first part. At this point, I'm pausing a little bit, trying to think about things that I have left out. Problems, collaboration, computation, and presentation. There were 4 slides, so the keywords are that this is a problem-driven course. We collaborate, we seek help if we need to. There is the computational aspect. After all, this is an MCS course. And the reporting is important. So these are the 4 points that I can emphasize now of the main importance of this course. All right, second part on Julia and the Jupyter notebook. So Julia is a new programming language, but already in a very stable version. So if we have used, in last semester we were using 1.6, most likely you will not know, or you will not see the actual difference in the language between 1.6 and 1.7. So but 1.7 will be the official version for this semester. Installing is pointing and clicking. I do not want to minimize this. I also have to, for myself, I have to sit down and very carefully pay attention of what it is that I'm doing. So there are 4 steps here. The 4th step is the adjusting of the environment variable. From somebody from my generation, I still like to use a terminal window when I'm on Linux or on a Mac, or on Windows. I very much appreciate the PowerShell. So if you want to run your code just by typing in Julia, then you have to set the path. So Julia is a programming language with a very large ecosystem. So the lines between a scientific software system, a computer algebra system, and a programming language are starting to blur. So that is another advantage. The other aspect, so we have Julia, and then we have the notebook. The notebook serves two important aspects of computation. The first one is documentation. In a notebook, you have markdown cells that contain text, also LaTeX. If you took writing in the discipline Math 300, then, or perhaps even earlier in Math 215, you may have been exposed to LaTeX. In markdown cells, you can also view and display LaTeX. So it can also be the first draft or even the final draft for your technical report. So investing in using the notebook well is an investment that definitely pays off. The other aspect is visualization. So there is the documentation and the visualization. Pictures often say a lot more than 1,000 words. To install the notebook, you first need to have installed Julia. Julia is case sensitive, so using iJulia, U with a little u, I with a capital I, J with a capital I. You may also have to be able to build. Again, I do not want to minimize installation issues. Even I, or perhaps just I, skipped the build stage, and then if you are upgrading for a new version of Julia, you will see that your notebook does not offer the latest kernel. Can be quite frustrating. So there is a first exercise. It's called exercise 0 because I can't really collect it. But the goal of the exercise is to get familiar with the latest version of Julia and the Jupyter notebook. If you feel that you shouldn't install anything, then I won't contradict you. Please make an account on CoCalc. There is no textbook for this course. Consider also, in that case, consider contributing, making a contribution to CoCalc as well. That gives you a subscription and gives you special privileges and priorities. Bottom line here, please contact me if you need help. So the main point of taking this course is that you have access to me. I have prescribed office hours, but you can also make appointments. I will try to answer emails promptly, and as best as I can, we can make online Zoom appointments if you have any questions or concerns. So this ends the second part of this pre-recording. If you have not taken MCS 320, if you have not taken MCS 471, then at this point this is a lot to take in. Jupyter, if I haven't explained this, Jupyter stands for Julia, Python, and R. So we are evolving towards more language agnostic computing environment. So Jupyter, Julia, Python, R, and many others. So we will be executing some Fortran code in this lecture. It will not be obvious to us that it's Fortran code, but I will, if I not forget it, I will point it out. So again, if you are new to this, there is a lot of information coming at you. We will see plenty of examples. And there will be plenty of time to catch up. Even if you're looking at this pre-recording, say, if you're thinking about enrolling this course at the end of the second week, do not worry. All right, so now we will solve 4 problems applying statistics. So we will run simulations. On Friday, we will do Monte Carlo simulations. So we will represent the outcome of an experiment by some random variable, asking the question, what is the probability that the outcome is a particular value? So we have a probability function. And we have a cumulative probability distribution function f. that asks for the probability that the outcome is less than the given value. Calculus looms here in the background, so there is the relationship between the probability and the cumulative density function. The words here have all very important deep meanings. We will illustrate them, or they will be illustrated on actual problems. So in some senses, it's a kind of a odd slide. This is a mathematical slide that kind of pops in, that sets the stage for what we are currently going to do. We're looking at 4 problems. So let's look at the outcome of a game. So we are rolling a fair 6-sided die. 6 possible outcomes, 1, 2, 3, 4, 5, 6, all equal likely when we do one roll. What is the expected value of the sum? So suppose that we would be designing a game. What is the expected payout? Also, if everything is equal probability, sounds fair, what is the expected variation in the outcome? So designing games, gaming industry is quite important. The answer here is the discrete uniform distribution. So, and I will be straightforward with you. The problem is actually not the problem. The problem is for me to introduce one of the important distributions. The discrete uniform distribution. So again, the setup, we have 6 possible outcomes and they're all equal probability. If we don't know what is the correct outcome, let's take the middle, which is not intuitive already. So the whole point of statistics, it's extremely useful, but also there are some intuitive ways of thinking. It takes some use to. So 3.5 as the outcome of a throw is absurd because there is no 3.5 side, but that's very useful to take the 3.5 to have the accumulation of 10 rolls. 35 is the expected outcome. So if we would attach a monetary value to the result of this outcome, then 35 could be the expected payout of the rolls. But now predictability is important. So in the next lecture on Wednesday, we will see how to define quality, and predictability is important. So we will introduce you to Takeuchi quality control. And actually it turns out if you would use a discrete uniform distribution, you would be expected to pay 35, but actually the variation is huge. And I confess here that for the second part I had to look it up. I will list the source at the end of the slide. So it turns out that the variance of one roll is quite large, 2.9. So you can expect 3.5 and 2.9, which is absurd again, because subtracting 2.9 of 3.5 gives you 0.4, and there is no 0.4 value, and there's also no 6.4 value. So, but intuitively here, you have such a large variation because every outcome is equally probable. Very unrealistic. But this is a first mathematical model. So rolling dice, good. So here is our first exercise. So again, often if things are looking quite strange, do an experiment, do a computational experiment. So part of the exercise could also be see that the variation of the previous example is really that large. Here we roll a pair of dice, so we expect an outcome of minimum 2, maximum 12. What is here the outcome of 1000 rolls, and you don't need to roll the dice 1000 times. Now here you see the computation, how good this is. We can just write a loop. So in Julia there is the built-in rand, and if you give it an input a tuple, the outcome will be one of the elements in the tuple. So if you run this command, you will see either 1, 2, 3, 4, 5, 6, and you store the values in an array. So in some sense this is a introduction to computer science exercise. Make a frequency table, a histogram. So I will not illustrate this today, but I hope to be illustrated at the latest by the end of the week, by lecture 3, the stats plots of Julia. So in some sense, by the time it comes to collecting or handing in this exercise, you already know how to make a histogram with stats plots. You can, if you are in a hurry, you want to solve the exercise today, just make the drawing on paper. And also, the purpose of this exercise is to see the cumulative distribution function. What is the probability of having, so you now expect 70 as the outcome, expected outcome. What is the probability of being unlucky, having less than 20? Or what is the probability of being really lucky and having more than 100? And, or if you do, if you do 10 runs, you would expect 120. So the cumulative distribution function helps you answering problems like this. All right, this is our first exercise. Mainly do some runs with Julia and make the histogram. So the histogram of one dice will be extremely boring because every outcome has the same probability. So the histogram of one die will be just a flat line. You expect the number of times you hit 1 to be the same as the number of times you hit 6. With 1000 simulations of a pair of dice, so when you take the sum, you will see that the probability, the number of outcomes of having, say, 2 and the probability of 12 could now be the same, but it will be different of having 6. So you will intuitively expect that you will see a spike at the middle values. So in some sense, rolling a pair of dice is already a more interesting probability density function. Second problem is the lifespan problem. We buy a bulb in the store, and the box says the expected lifespan. So here you expect to have 1000 hours of light in there. Sometimes the standard deviation might be on there, but you may have to be able to look it up or to guess it. So suppose here that on average we have 1000 hours, but a normal bulb will give light between 600 and 1400 hours. This is how you should interpret the standard deviation. Now what is the question now? Assuming that normal distribution, assume that you have a normal bulb, what is the probability that you have a bulb that is really, really extraordinary and lasts 2000 hours? So we will define quality more precisely in the next lecture, but let's think about this question now. And the answer lies in the normal distribution. So what is the normal distribution? So here it's answered with a picture. First important thing that you may observe is that we have the numbers 1 and 0.4. So instead of 1,400, I've normalized the numbers, although normal distribution is typically average 0 and standard deviation 1. So I have not normalized it that far, but from numerical analysis you should have the instinctive reflex to scale it down to smaller numbers. Smaller numbers are better numbers. So here we plot this for 1 and 0.4. So in blue you see the complicated formula, or the natural or the normal bell-shaped normal distribution. What does it mean to be normal? Well, it means that you are between the green lights, the green lines. So in between green, if your light bulb lasts between 600 and 1400 hours, then you have a normal bulb. So that is the normal life expectancy here for this type of bulb. And we are interested now where the red is. When can we expect, what is the probability that we have a light bulb that lasts 2000 hours? Twice as long as what the manufacturer promises as average. Alright, so this is essentially the answer. So the answer will be the area, or 1 minus the area under the blue curve, starting from 2 till the end, although the end can already be at 3. You see at 3 we have already 0. Alright, the answer is using numerical quadrature. In MCS 471 we spend an entire week on techniques. So here what is mostly important is that you find the right software for doing this. So I looked around very briefly before I did this computation, and in my opinion the integrator from SciPy, which now actually runs the Fortran black box integrator in QuadPack, Fortran 77. So this seems to be still kind of the software that I prefer and also trust, because it gives us an error estimate. So if you look at the outcome, what Quad gives us, it gives us a tuple of 2 numbers. The second number is very small. In numerical analysis, we read the numbers from right to left, and the numbers are in scientific notation. So you see the e minus 15, which is 10 to the power minus 15. So I do not want to trivialize this. There are a lot of things that can go wrong. If you type in using SciPy in a very clean first installation, it will not work. You have to be patient. And if you are offline, if your computer is off the internet, it will not work at all, because it will request you to download some software. So the package needs to be downloaded and needs to be installed. So the using SciPy, if you do this the first time, is not a trivial instruction. The second line, so here this is done in using Julia as a calculator. The second line is actually also not so trivial. Well, again, defining a function is simple as it can get, but notice all the brackets. So you have 1 over the standard deviations times the square root of 2 pi. Note the round brackets. Some things may go wrong there. Be patient. Be patient. Then there is the third instruction, which is asking for the normal distribution. So statisticians, so you can say, what is normal? Well, normal, you're like everybody else. Well, normal is that you are like 68% of the population. So here the 68 is illustrated with this value of this integral. If I integrate, so the probability between 6.6 and 1.4 gives me the 68% here of what it is to be normal. And our answer is what is the probability now that we have a light bulb that lasts longer than 2000 hours. So I integrate from 2 to 100. I adjusted the 100 a little bit to have the error less than, make the error very small. Although you can see that 14 decimal places is overkill, as we need only 2 decimal places. All right, we have a tiny probability that we have a very, very great light bulb that lasts 2000 hours. Choosing the right distribution is important. Finding the right parameters is a problem as well. So with this example here, it's really an example. It's not a problem that we have solved, but it's an illustration of how things come together. The formulas, the model, and the computations, and then the interpretation. Also verifying that your computations are correct, and also verifying then later that your answers are actually realistic and plausible. The validation aspect is also important. Okay, next exercise. So suppose you have a friend that's kind of adventurous and outdoorsy, not so much of a nerd, but he's planning a bike trip, motorbike, through the desert. It's about 1,000 miles, and the tires, it's a rough terrain, and one estimates that the expected span is about 1,500 miles, and a standard deviation of 300 miles. So your friend knows enough to guess that 1,500 minus 300, well, it's gonna work with 1,000 miles. Why not? They're fresh new tires. But of course there is the risk. So you're in the desert, and as soon as the tire is up, you can't really go on. So your trip is over and you're stranded. So your friend asks you, what's the probability? Is it actually now really a good idea to go out there with this specifications? Should I be worried? Or especially because you are the friend, should you be worried that you have to rescue your friend? So it's also the lifespan problem, but then asked in a different way. There are no dollar amounts on this question, so instead of having this as a simple innocent story, imagine that instead of your friend, it is a customer, and you are the insurance agent. You have some problem, some undertaking that involves risks. So there might be a reward, so it could be that there is a prize associated on completing the motorbike trip. Could be that your friend is sponsored by some companies and takes all kinds of selfies and promotional videos, so there is an outcome there. But there's also a risk. If you're in the middle of the desert, in the middle of nowhere, really, there is a rescue mission. So what is the price of the rescue mission? Is it worth the risk? So this could also be a topic for a project, second project cost-benefit analysis, or again, if you like, the data, what is the proper model for an adventure such as this. Here we solve this with the normal distribution. All right. Second problem, here you are a manager. say in a store or in a warehouse, and you need to schedule staffers. So you have number of employees, and if you email them, they are aware that you require their presence for the shift. But you know from experience that only 1 in 3 shows up. So how many staffers should you email? So sometimes you make up your schedule the evening before, and not everybody reads their email for the next morning, the shift in the next day, or some people have already prior commitments and cannot come. So how many staffers should you email to guarantee that at least 20 will show up? You would think 60 might suffice, but it's not such a great answer. We will see this is not the correct answer, especially not if you want a confidence that with 90% confidence, so with probability 0.9, you have that 20 people will be there to staff your shift. All right, here is the solution as a formula at the bottom. Again, I do not want to... So this is an example of the binomial distribution. So what is the binomial distribution? So it's modeling also a coin toss. You're sending out an email, and with probability 1 over 3, you have success. So your the person you sent the email to shows up. But you also have a probability of failure, and it's a loaded coin. So the probability of failure is 2 over 3. So for one particular person, is one person shows up, the probability is 1 over 3 times 2 over 3. Now, the probability that k people, or here in this case 20 show up, is all possible sets of 20 of the total number of emails that you have sent out. So I'm already presenting you the answer here. It takes some time to see that what the question really is. So the unknown is here in kind of an awkward position. It's the n in the n choose k. So the number of emails you have to send out is the unknown. And if you look at this from an equation, it's an inequality. If you want an exact answer, it might also be kind of hard. So having computers to help us is really a benefit here. So doing this with pen and paper is not that good. But the important part here is translating the problem in the correct model. And again, it's an example of the binomial distribution. It might very well be, and it is so, that this is an oversimplification. All people are different. There are people, whenever you ask them something, they will do it. So the 1 over 3 to them would be an insult. And there are also people who will do things whenever it suits them. So the 1 over 3 might be too large. So it could be another data science project to come up with a good model for this. Also, it assumes here that everything is independent, but people do not live in isolation. It could be that some people will only show up to the shift if some other people show up, or if they will not come if that person will come up. So the whole managing problem is an important problem in logistics. So this could be, if your calling would be to go into logistics, into scheduling, then this could be a starting point here. All right, so what is now the computational solution? It's a one-liner. So in some sense, it's an advertisement for array comprehension. So if you took Python, and I'm sure you have seen list comprehensions in Python, this is very much Pythonic here. So we are using new languages, but new languages, they use also all the good things of other languages. So array comprehensions are actually a big thing. And speaking of big things here, there is the big. So Julia is using by default 64-bit floating point precision. And that might not always be enough, especially not where factorials are involved. So in some sense, this is a commingling well, it's actually not a commingling, it's a forcing Julia to work exact, although it still gives you point answers. The point here, the main point is that 60 is not enough. So if you send out 60 emails, if you call up 60 of your staffers, then the probability that you will have 20 is 45%. And here you see a little bit the absurdity of using exact. I only want 2 decimal places. But please try this without the big in there. So you will see that the answers are different and not really right. So the right answer under the assumptions of the model, the binomial distribution with the parameter 1/3, if you take that as a given, then you need to send out at least 74 emails. So that's one cog in the wheel in an entire project. So we will see Monte Carlo simulation where you can now run all kinds of what-if scenarios. So what if the probability is not 1/3? What if there are 2 groups of people, the dependable people and the not so dependable people? How do you run a simulation like this? Here is another idea for a project. Overbooking. If you are the victim of overbooking, it seems an extreme injustice, but most of us have probably been the beneficiaries of overbooking because it allows airlines to fly full airplanes and it makes airline tickets quite affordable. So here is the problem setup. On average, we take 5% of travelers who do not show up, change their mind, or arrive too late. There are all kinds of reasons for that. So the 5% is a number that I plucked from the air. So knowing that as a planner, how many more tickets then can you now sell? More tickets than the available seats, and still give everybody who shows up a seat. So you could work with a simulation. But the suggestion is actually that you adjust the numbers for the staffing problem. So translating here, the probability that somebody does not show up is in the 5% here. You have to translate that information. So now we have 5/100 instead of 1/3. We had the number of emails that were sent out. Here you want to know the number of tickets that you can sell for a fixed number of seats in the airplane. So that information is not given, but you can work, say, with a fixed number of 100. Sounds like a good number for seats that you could sell. Again, the purpose of this exercise is that you look back at the binomial distribution. But it could be a project. So again, it could be a first project in acquiring the data. So, and the government has a lot of data. It could be that there are actually public databases out there that give you some motivation for the 5%, or you may have a similar problem for which there is data available, and also on the type of distributions. In the second part of the course, we will do cost-benefit analysis. So there are dollar amounts. For every person that you have to turn away, you have to give a compensation, or you have to give a first-class seat. That costs you. So how do airlines actually do it? So you could also check around in the literature. But what is also important here, what is the mathematical underpinnings for this? All right, I get now to my last problem, and I see I have 5 minutes left. I do never want to run over time, or I'm already probably running over time. I apologize for this. So here is the arrival problem, which illustrates the Poisson distribution. The 20 numbers comes again in. So on average, we have one customer per minute, or 60 customers per hour who check out. What is the probability that you have a spike, that all of a sudden, say it's rush hour, you would have 20 customers check out in a quarter hour, in 15 minutes. So that will be answered by the Poisson distribution. What is critical here is that it is a continuous distribution. Time, if it involves time is continuous. It's suggested perhaps that you work with hour as a time unit, but smaller numbers are better numbers. So quarter hours, 15 is a better number. So your time unit is 15 minutes. With the Poisson, we have our parameter lambda, which is 15 here. We have the probability distribution and the cumulative distribution. And we have a formula. So the mathematical model gives us also the mathematical solution. Sometimes you can actually think backwards. What is the answer that you want? And then what is the mathematical model that you can afford? So the mathematical model that we can afford here in the time that I'm running out is actually only one formula. And we will evaluate it now with a Julia function. We can use an array comprehension as well, and that will be the last exercise. Here I want to illustrate the making of a Julia function. So we run this Julia function by running, you can run it in a Jupyter notebook by copying the code into a cell, or you can also run it so that it will be posted as arrival.jl. You can run it as Julia and the name of the program, and that will print the answer. When I teach programming, I almost enforce that every function is documented. Julia has its documentation strings before the prototype. So here it is a function that doesn't take any arguments, but what it does, it actually answers the question. It prints out the probability. So the probability is actually quite low, less than 8% that you have this spike. But you can see what it gets computed. It computes the formula, and the formula here is not necessarily the algorithm. So I'm going now to the exercise. In some sense, returning to the array comprehension. And you're invited in this exercise to play with the array comprehension. And by default, Julia uses 64-bit floating point arithmetic. If you took numerical analysis, or you're taking it in the first week, then your professor are probably going to tell you that adding very large numbers to adding very small numbers is not such a great idea. Actually, working with huge numbers is never a great idea when you work with a limited precision, even though 64-bit might seem a lot. It's not sometimes if the numbers start to grow exponentially. So the purpose is here, can you find the same answer? I mean, first of all, without the big, you will see that you will not get the same answer. Explain this. and try to fix it. You can also resort to going back to Sage and compute with exact arithmetic. Although notice that in the setting of statistics, where we often only need 2 decimal places in our probability, working with humongous numbers, think about the expression swell problem again in computer algebra and symbolic computation, may not make sense. Okay, I think I'm running over time in this pre-recording. Bad sign. I will list my sources. So I mentioned for the discrete uniform distribution that I had to look something up. The UIC library provides a lot of online resources. This could be a resource that could be useful for later projects. We give 4 major distributions, but actually there are 40. There are 10 times as many major distributions, and some of these distributions are tailored towards specific applications and examples. So this book gives these specifics of every distribution, more than actually you will need to know, but also you could see it as an example book. It lists examples where the distributions are used or occurring most often. Okay, thank you for sitting through this pre-recording, and I hope that the most important aspect what is this course all about has become clear. I hope that the setup, the computational setup, has not overwhelmed you, and that with the examples and the 4 exercises, I have given you an introduction of what potential projects could be. And with the airline overbooking, the staffing problem, the lifespan problem, the arrival problem, you can see that there are many very important economical implications of being able to solve these problems correctly, or at least thinking about them well. So I will stop here.